So in 6.4, we're going to continue with radicals. But now we're going to look at radicals that have binomial setups. What does binomial mean again? Binomial. What does that term mean? Remember we talked about vocabulary, how it's important? What does binomial mean? 2 terms. Good. Trinomial, 3 terms. After that, do we go any further? What do we start using with the word? Polynomial. Poly meaning many. So we have binomials here, so we'll have 2 terms. 2 terms are separated by what operation symbol usually? One of 2 answers here. Terms are separated by what operation? What operation?
Addition, subtraction.
Very good. Remember, if I have 2 things multiplying, are they called terms? No. What are they called?
A term?
Together they're a term, but the 2 things themselves, if they're multiplying, they're each called what? Factors. Okay? So we have to separate our terms. We're looking at binomials here. So let's jump right into it. Remember with variables, when you had binomials, what did you do? You used distributive. Whether it was double distributive, triple distributive, etc., etc. But then we came up with this idea of FOIL, and a lot of you know of FOIL already. So here, we're going to see binomials being multiplied or divided, and thus we're going to use FOIL inherently, but really what are we doing? Double, triple, quadruple, whatever distribution. Okay, so let's get right into the first example here. So for this first one here, all I want you to do is FOIL it out like you would FOIL a binomial. Okay, operate on the first one the same way you would on a standard binomial. So if we take a look at this, we've got 4 times 5 first, giving us 20. That's first. Outer, I've got 4 times negative root 3. So negative 4 root 3. Inner is going to give me root 3 times 5. When I do root 3 times 5, I'm going to get 5 root 3. And then last is going to be root 3 times root 3, which is just?
Negative root 9.
Yeah, negative, in this case it's negative, but root 9. Very good. And we know root 9 is simply 3, so you could simplify. So this process you're recognizing right away is rather simple. It's very similar to what we did with quadratics, and we had to multiply. Then we subtract 3, we get 17 plus root 3. Okay, so take a look at your combining like terms stage. Here, how do we think of this again? What did I tell you guys in the last lesson? What did I say to treat this like?
Like it wasn't variable.
Yeah, very good. So if it was negative 4x and a 5x, I would combine like terms, right? Negative 4x and a positive 5x is simply 1x. So I really have 1 in front of here as a coefficient when I combine these like terms, bless you. And then the root 9 becomes a 3, and we see that 20 minus 3 is really 17. Bless you. Questions on the first one? Can we skip number 2 and go to C? Why would C be a little bit trickier? What do you have to do with C? What do you have to remember?
Turn it into 2 instead of just...
Good. You got to turn that into 2 parts. You can't just distribute the square to both terms. The square only gets distributed to factors, not terms. So let's jump to C. Okay, so we have 2 root 3 minus 4 root 5 times 2 root 3 minus 4 root 5. So I'm just going to cross off that square now, because that's what I should be thinking about. I should, again, be multiplying these 2 things like I'm foiling. So you're going to FOIL the first, you're going to multiply the first, outer, inner, last. What's the key here? Why is this a little bit trickier than the first one we did? What's the only real difference that you're noticing? Justin, what do you got?
You have root 3 root 5, so root 3 and negative 3.
You say it one more time?
You have root 3 and root 5 instead of just root 3.
Okay, that's one thing right away, yeah. You have 2 different roots or 2 different radicands under the radical, very good. What else?
There are roots in every term.
Roots in every term. What else? The roots also have what in front of them now? What is that called? What's in front of each of these roots? What do we call that? Something that's in front of something. What's the word for it? Coefficient. Very good, Max. Coefficient. So these roots not only occur in every single term, but you have coefficients. So some students struggle with this because like, oh, what multiplies what? But who remembers? What did I tell you yesterday or the other day? I gave you a quick, simple thing to remember. Anybody remember?
Multiply inner to inner,
Outer to outer, inner to inner. Remember that? So when I'm multiplying 2 root 3 times 2 root 3, it's going to become 4 root 9. Bless you. Is that clear what I'm saying here? Okay, don't mix up what's on the outside with what's on the inside. And how do you remember? As Bridge told us a minute ago, think of them like variables. If I had 2x, I'm going to give you a hypothetical. If I had, get rid of that line. There we go. If I had 2x times 3y, the answer is simply 6xy, or the simplification. Because the 2 and the 3 multiply, because they're coefficients, and then the x and the y multiply, they are the variable terms. It's very similar in what we're doing with part C. So when I take 2 root 3 times 2 root 3, I'm going to get 4 root 9. After that, I start taking 2 root 3 times the outer term, which is negative 4 root 5. So I do the 2 times the negative 4, giving me a negative 8. And then root 3 times root 5 is root 15. And I go to inner. For inner, I take my 2 root 3 right here and multiply it by my negative 4 root 5. I think of both of these terms here. Okay, one is positive, one is negative, so I have to have a negative here. On the outer part, again, I'm going to get 8 root 15 on the inner part. Why are these the same? Why are they the same? Okay, because they're multiplied. When we look at the operation, they're multiplied by the same thing. But there was another reason. Why did it come out to be multiplied by the same thing in the first place? What caused that? What's the cause of this?
Conjugates?
They're not conjugates. Good idea, though. If one was positive, one was negative, kind of thing with conjugates. They're not conjugates. What do we have here? We have a difference or a sum to a power. Whenever that happened, there was a thing where the middle term doubled. The middle term always repeated itself whenever you squared a binomial with variables. Well, this is the same thing. If I had x plus 2, that quantity, and I square it, I'm going to get x squared plus 2x plus the 4. The 2x and the 2x is not a coincidence that they're the same value. It's because you're squaring a binomial. So this middle term here is always going to be the same when you're squaring a binomial, even in the case of a radical involved. And then the last part is going to be, I'm going to take this 4 root 5 times 4 root 5. They're both negatives, making that a positive, and that becomes 16 root 25. So when multiplying C out, that's what you're going to get. Now, it seems like it could be a little confusing because we have many different radicals, but what do you notice right away? Those radicals, some of them are what? Right off the bat. Some of those radicals?
Perfect squares.
Why are they perfect squares, Luke?
Because the same number multiplied by itself.
Exactly. Whenever you take something like root 3 times root 3, or root 4 times root 4, any of those, you're going to get a perfect square because that's what a perfect square is. It's the same number multiplied by itself. So as a result, you're going to end up with perfect squares here. Just reduce those, please. Okay? What do those look like reduced? I'll put it at the very bottom. We'll continue down here at the bottom. 4 root 9 is going to be really 4 times 3, which is 12. 16 root 25 is 16 times 5, which is 80. So those two are done already on the outer parts. And then negative 8 root 15, negative 8 root 15 is negative 16 root 15. I'm doubling that value. So my answer becomes 12 and 80 gives me 92 minus 16 root 15. Okay? How about the last one? You already got it? You already see what's happening here?
Difference in t-squares.
Very good. Awesome job, Tristan. So a couple of you I'm sure went ahead already, right? You like to go ahead and get the other ones done, which is good. And you'll notice here that it's difference of two squares. It might not be obvious, but it sure is. When you have difference of two squares, when you have conjugates, x plus 2, x minus 2, x plus 4, x minus 4, a minus b, a plus b. Whenever they're conjugates, you end up with difference of two squares as an answer. And when that happens, what happens to the middle terms?
Oh, they disagree.
It always cancels. So right now, for part D, you go up so you can see it at the very top there. For part D, you're multiplying binomial conjugates. The middle terms will absolutely cancel. So should you do them? If they're going to cancel, do you have to do them? No. Take the optimal route, please. Don't take extra time, especially when things are timed. Everything in life is timed, right? Your tests, your subject tests, all this stuff, AP exams. So you would not multiply out the O and the I from the FOIL. All you got to do is the first and the last. Outer and inner are guaranteed to cancel when you're multiplying binomial conjugates. So as a result, 2 root 5, 3 root 7. Okay, let me write it down here. Okay, so here's our problem for part D. As a result, when I multiply the first part of FOIL, I get 4 root 25. When I multiply the last part, I get negative 9 root 49. The inner goes here, and the outer goes here, but what happens to them again? Cancel, cancel. They cancel with one another. So this is what I'm left with. 4 times 5 minus 9 times 7. What happens? The answer goes from being an irrational beginning to what kind of an answer? Completely rational. So you take something that's irrational, like 2 plus, or whatever it was, 2 root 5 minus 3 root 7, and by multiplying by its conjugate, the answer becomes rational. Why might this be a useful technique? Why might this be a useful technique? Come on, people, think. Use your context clues. What have we done in the past that involves making something rational when it was previously irrational? We just did it like a lesson or two ago.
Or like the rationalization.
Good. Rationalization of a denominator. Remember, if I have like a radical 5 in the denominator, we multiply by like radical 5 over radical 5. Well, now, what if you have a binomial? Binomial with a radical in the denominator. That's the question I have to pose. Okay? So let's jump right into example 2. Next slide. This next slide here shows us 3 examples. And all of these examples involve binomial radicals in the denominator. So what should you do to make it a rational denominator? Multiply by the, what's the word again?
Reciprocal.
Not reciprocal, what do we use?
Radical.
Not radical. We need our vocab. Like, for example, the first one, I'm going to multiply by 2 plus root 5 over 2 plus root 5. Because the last example showed me that that would become a rational number, right? What is that called again?
Irrational.
Yeah, but what am I multiplying by? I'm multiplying by its what? Conjugate. Thank you. Conjugate. I heard reciprocal, conjugate. Opposite the word is conjugate, okay? So multiply by 2 plus root 5 over 2 plus root 5. Now, if you don't believe me, and you want to go back and think, oh, just all I need is root 5, really. Because, yeah, I've got a root 5, multiply by it. You're still going to end up with an irrational denominator if you only multiply by root 5 over root 5. It's got to be the binomial conjugate when you have a binomial in the denominator.
Why is it plus root 5 instead of...
What does conjugate mean?
Oh, you switch the sign.
Think about. Go to the last example. Scroll up, please. Look at part D. Weren't those signs opposites before you multiply them?
Right.
Binomial conjugate is an example of dots. Dots gives you factors like x plus 2 and x minus 2. What do you notice? The signs are opposite. Conjugate is the part that means opposite.
But then why does 2 turn negative? Why isn't it negative 2 plus 1?
Because only conjugate means switching the middle. So whatever operation is occurring between the two, not in front of the first number. Okay? So it's not, I see what you're saying. You're not negating the entire thing, Tristan. You're switching the middle sign. How do I multiply the numerator? Let me start with that. 3 times 2 plus root 5. What does that give me? George?
6 plus 3 root 5.
So George, what operation did you use there?
The
What property?
distributive.
Good. You got to distribute. Got to distribute. Got to distribute. If you didn't get that answer, write yourself a big note. You have to distribute here because you're multiplying 2 or 3 rather times the whole quantity, 2 plus root 5. So what might you do to make sure of it? Here's what I would do if I were a student. Okay? Take a look at what I'm doing. Look at the original problem at the top now. See what I did? Why did I do that? What does it remind me to do? It reminds me to FOIL the bottom and to distribute the top. See what I'm saying? Okay, in case you didn't write that down or in case you got that wrong just now in the numerator, write yourself a little note. Put parentheses around everything like that. And that will remind you to distribute or FOIL. Denominator, am I going to do the middle terms? Am I going to do the middle terms? No. Again, foiling, the middle terms cancel. 2 times 2 gives me 4. Negative root 5 times positive root 5 gives me negative root 25. Keep simplifying this. The numerator is still 6 plus 3 root 5. The denominator, though, now is 4 minus 5, which is negative 1. So I can leave my answer like that, or maybe if I want to write it as a or make it look like it's not a fraction, I can write it like this. Okay, either way is fine. But do you see what happens? 4 minus 5 gives me negative 1. The denominator becomes rational. Hence, we call this rationalization, right? Rationalization. Questions on this so far? Are B and C any different? You're already on. I see a bunch of you on B and C, which is good. Are they any different now, really? No. I mean, the numbers are different. The processes are the same. But you recognize that your numerator needs to be foiled now. You got to foil the numerator and the denominator for part B and C. Oops. And what did I do? I made the common mistake just now. Look what I started doing. I started writing 4 plus root 5 when I should have been writing 6 minus root 3. What did I use accidentally right off the bat? What did I just do? I used the conjugate of the... Yeah, it's only the denominator, okay? Even if the numerator itself is irrational. It's the denominator that we multiply by, its conjugate, simply because we want to rationalize the denominator. So that's what we're multiplying by. So up top, you got to foil that. You got to foil down below, but ignore the outer and inner. But up top, you can't ignore the outer and the inner terms anymore. On the top, I got 4 times 6 is 24. Outer is 4 times, right? Here's the outer. Let me point to it. 4 times the negative root 3 right there. So it's going to be a negative quantity, and I'll put negative 4 root 3. Inner, I'm going to multiply 6 times negative root 5, so that's going to be negative 6 root 5. And then last but not least, negative root 5, negative root 3 gives me a positive root 15. The bottom, though, again, when you multiply out the bottom here, there's no need to do the middle terms. On the top we had to because you can clearly see that they differ. But in the bottom, the middle terms will be identical. So I'm not going to multiply them. That's what the bottom becomes. And then just simplify. 36 minus root 9 is really 36 minus 3. The denominator is simply 33.
And we can't simplify the top.
Well, I was about to ask you that, Tristan. I was going to ask all of you that. Is there anything you can do on the top? Can you break up 15 into anything with perfect squares? No. These are done. Are these like terms? Can I just say, 6 and 4 add up. 3 and 5 add them up. Why can't I add these together? What do they have to add together?
The same number inside the...
Very good. The same radicand. Very good. The same number inside. And then 24 on the outside is just hanging out there. Now, hypothetically, I could divide 33 into everything. But it's not really that useful because only 24 and 6 would be divisible because they're factors or multiples of 3. But 4 is not a multiple of 3. The 1 in front of the 15 is not. So it's really no use going further. But I want to show you so you can see it, so you understand what I'm saying. So if I divided the 33 into all of these, it would look like this. Remember, a monomial into a polynomial numerator divides into everything. Now, the only reason one might do this is if it was able to simplify a little bit further. But here it's like, it's a waste of your time. Okay, it really doesn't make any difference whether you have it written one way or the other. This becomes 8 over 11. Still, minus 4 root 3 over 33. 6 over 33. Divide them both by 3. You're going to get 2 over 11. The root 5 stays in place. And then at the end, you can't divide that because one's on the outside and one's on the inside. So only I can cancel here, right? Again, 24 over 33, reduce them by 3, becomes 8 over 11. 6 over 33 becomes 2 over 11. That's all I can do, but it's not really necessary. All right, I'm going to leave the last one for you just for the sake of getting into the project. The last one is not any more difficult. If you could do it though, like I'd practice this one. Your homework's going to have something like this also. You just have a lot of square roots now, right? So the last one, you don't have to worry about any coefficients in the front. So once you FOIL everything out and do all that work, just make sure to try to simplify wherever possible. Okay, so I'm going to cut it.